Well, hey guys, and welcome to another video. This one is a temperature measurement without the control, just a temperature measurement. There's still plenty of room in this PLC unit for the control. For this, I'm measuring temperature without a temperature module. All I'm adding into the PLC itself is one 10K ohm resistor and one thermistor. This is an analog PLC unit. I'm measuring the temperature, and this one I set up for a range of measurements from I believe 50 degrees Fahrenheit to 140 or 150 degrees Fahrenheit. It's a simple program. It's only about 14 rungs or 15 rungs, something like that. But what's really good about this program is it's a perfect example of using a for next loop and pointers to increment data addresses as you go through, especially when you're searching for a value that you've already have set in there. Now, I did have to use a spreadsheet to come up with the values that I wanted to put in, because I needed to know what value I expected for each temperature at the analog input. So that's just simple Ohm's law, but I showed you how to do that in this video, and also used a spreadsheet so that once I developed the one time, I could just grab the value and just drag the value straight down in the spreadsheet. Now, for this, I did need to buy some thermistors. I didn't have any thermistors, so I think this was about $11 or $12 from Amazon, a pack like this, and it's 100 thermistors, and it's 10 different values, so it's probably 10 of each value. And I already had a pack of resistors, all types of values. This is 600 pieces. I've had this for a couple of years. I just used it occasionally, but I want to say this was about $10 or $12 about 3 or 4 years ago when I bought it. I'll give you a link for this one if it's on Amazon still as well. The reason for this video came from a subscriber that had a question about how to do something, and I thought about it and I realized that there was a way to do it, and I thought this is a perfect example for another video. So that's why I made the video. So if you come across a problem that you've got that you think that I might be able to come up with a simple solution for, but usually I can help you out by at least pointing you in the right direction. Anyway, enjoy the video, take care, God bless you. I'm in my shop right now, and I made something very simple to measure the temperature. I display it here, and right now the temperature is bouncing between 80 and 81 degrees. It's not bad. But I'm measuring this using just a click PLC and a 10K thermistor and no temperature module. My setup is real simple, but if you're an OEM, you want to keep the expenses as low as possible, especially if you're going to make 30, 50, 100 of something or 1,000 of something. You want to keep everything as less expensive as possible. Temperature module is not cheap. They're fairly expensive. But on this standard analog PLC, I have 2 analog inputs, 2 analog outputs. I still have 4 discrete inputs and 4 discrete outputs for my controls. So let me show you how simple this is. This is a 10K ohm thermistor, and it's connected to the analog input, but it gets its power from an analog output, 5-volt power. All right, also from the analog input to analog common is a 10K ohm resistor right here. I don't know if you can see it very well. Physically, that's all there is connected, other than the 24 volts for the PLC. But this display is only something I connected to make the video. Normally, for this, you would probably just use a data monitor inside the PLC software. So now let's go into the PLC program. You can see in the main program, I only have 3 rungs of instructions. The first rung is simply telling the analog output to go to 100%. This provides 5 volts VCC for the thermistor. The second rung converts the analog input from percentage of input to voltage, which we will use later. And the last one is just to call the temperature subroutine. So this part of the program is extremely simple. It's going into the temperature subroutine. Here I have, let's see, before the return, I have 8 command lines, or 8 lines of instruction, and that's all. So the program is not very difficult. In the first rung of the temperature subroutine, all I'm doing is I'm putting in an initial value into the temperature raw value. The second rung loads a value of 100 into the pointer address that we'll be using to in the for next loop to check from one value to the next value. The third rung, let me slide down a little bit. The third rung is the beginning of the for next. Now the for next is a loop. It will continue looping for as many times as we tell it. So here I'm telling it 90 times because I'll be checking a maximum of 90 different temperatures. And inside this for next loop is where I do the verification and testing to see what the temperature actually is. And then the for next loop ends on rung number 7 and rung number 8 if we have an offset value because the raw value of the temperature is not exactly, maybe it says 78 degrees, but the real actual temperature measured is 80 degrees. So in that case you would have a temperature offset of say 2 degrees. And this is where we sum the two together to give the true temperature. And right now this is in monitor mode, so you can see that I'm measuring a temperature of 81 degrees. This for next loop is what's doing all the checks. Now it will do it 90 times. Like I said, it'll check 90 different times whether it finds the correct temperature or not. There's not an exit for it. Now this is where the PLC work is done, but where your work is done here is when you have to set up the data, the values in the data view. The first part of the data view is for my information so that I can verify that things are working correctly. The first one is a DF10. That's the output value I'm putting in to the analog output. I'm putting a value of 100 in there. DF1 is the physical analog input, and you can see there it's reading percentage of input voltage. So it's reading 43% of 5 volts. The third line is DS3. That's my pointer. The next one is DS10, which is my raw temperature. This is the raw temperature that it found going through the for next loop. And then if I have an offset value, it shows up here. And the last rung of the temperature subroutine adds the raw temperature and the offset temperature together, and they become the actual temperature, the temperature F. Now all these others, from DF100 all the way down to DF97, are values that I'm putting in right here by the new value. These are values that I'm putting in that correspond to a temperature reading. Now if I go back to DF100 here in the data monitor, you can see I gave it a nickname of F150 because this is the voltage that would correspond to 50 volts, because this is the voltage that corresponds to 50 degrees temperature actually measured going into the analog input. And then the next one is 51 degrees, 52 degrees, and so forth. But these values have to be calculated. And what I do is I calculated all these values in a spreadsheet, and then I manually put them in. Now it sounds like a lot of work, but if you're doing a home project, it's not so bad. You can shorten down the temperature range so you don't have to put in as many values. Let's go back and look at the physical structure of what we have and why I have to come up with these values. Looking at what I've got connected to the Click PLC, you can see I've got one of the analog PLCs, and I'm using a digital to analog voltage output number 1 to supply the 5 volts to the thermistor. Now this is a 10K type 2 thermistor, and it's connected into the analog to digital input, voltage input number 1, and also in parallel with this input is a 10K ohm resistor going from this analog to digital input to analog common. Now that makes an equivalent circuit of this one down here at the bottom, because here you can see I've got the 10K thermistor. I'm getting a 5 volt supply from the digital to analog output, and the thermistor is connected to the analog to digital input number 1, and it with a 10K ohm resistor to common. But now I'm showing also 25K ohm for input impedance. Let's go back and take a look at the manual. So going back into the PLC program, let's go to the function tab and scroll up to system configuration. There you can see which PLC I've got in the program here. I'm using a 02DD1-D. So alright, let's close this and go down to hardware manual. and go down into the, scroll down until we get to table of contents. Here we go. This one looks like good enough. This one right here. It's 251. All right, this is the PLC that we're using. You can see the analog inputs right here. It just shows typical connections for them. Let me scroll down to the specifications because that's what we really want to look at. All right, here's the specifications for the analog voltage input. So you can see the input range is 0 to 5 volts with a maximum of 6 volts DC. The resolution is 12-bit. 12-bit resolution means it's going to take that 5 volt signal that you have, 0 to 5 volt signal, and it's going to divide it by 4096. In other words, it's going to give you a resolution of about 1,000th of a volt. The next thing we're looking at is the impedance. The input impedance is 25K. Now it says if you've got one of these older ones and it gives you a serial number here, that your input impedance would be 150K. But what we're interested in is the 25K input impedance, 5 volts maximum signal, and the resolution. Take this information back with us. Let's go back to the drawing. We have plus 5 volts for the supply for the thermistor, and the thermistor is connected to the analog input. Then from the analog input to analog common, we have a 10K ohm resistor in parallel with a 25K ohm input impedance. So we need to make that an equivalent circuit, so we just have one resistor we're looking at to bring it over to what this is over here. This is the equivalent resistor. But how did we get there? I took the conductance of the 10K resistor and the 25K resistor that were in parallel. The conductance means how easy it is for current to flow, which is the opposite of resistance. So when I take the conductance, it changes from ohms to mhos. So this is those two values. Now, since I know what the conductance value is, how much current could flow through each one, then I can just add these two together and I come out with one single value. If I take that one single value of the two mhos added together and I take it back to ohms by taking the reciprocal, I now have a single resistor representing the input impedance. So now I can take this value right here and knowing what this value will be for the different temperatures, I can put this into a spreadsheet, which was easiest for me, to be able to calculate what the analog input voltage should be for each temperature. In this spreadsheet, I went ahead and I put my columns in for the temperature in Fahrenheit. This column is the thermistor ohms. This becomes the resistance of the input, my parallel resistance. This is my calculated resistance, the equivalent resistance, which we just showed on the other paper. This is the percentage it would be of the voltage applied, or the voltage input to the analog input. This is my voltage applied to the thermistor circuit, and this is what my actual voltage would be. If you haven't worked much with spreadsheets, there's some basics that are real simple and really help you out a lot. So what I did here is I put in the temperature. I started at 50 degrees, and I just drug this value down. I let it increment all the way until I got to 200 degrees. So that's all I did for the first column. On the second column was more difficult. I had to look at a thermistor chart for the 10K ohm thermistor and see what the ohm value would be at 50 degrees, at 51 degrees, at 52 degrees, and so forth. And I manually keyed this value in for each of these temperatures all the way up on my spreadsheet up to 200 degrees. Now, it didn't go all the way up to 200 degrees in the PLC. Then I keyed in what my input impedance was, and this is constant all the way through, and my parallel resistance, which is the same. And now my equivalent circuit is just like we showed in the sketch. It's the reciprocal of the value in C3, which is right here, all right, plus the reciprocal of the value which is in D3, which is the 10K ohms, all right. And then I take the reciprocal of both of those summed together, which is this, and this gives me my input impedance, which is 7.1428K. For the percent of VCC, I say I want to take what this value is here, and I want to divide it by the total value of this plus my ohms here to get the ratio of what it is of the percentage. That became the percentage of my supplied voltage. Now then, for the voltage in, all it is this value right here, whatever the percentage is, multiplied times whatever my VCC is, or the 5 volts that I supplied. Once I set up my formulas and I manually keyed in the ohms for the thermistor, then I was able to tell exactly what my voltage input was. So then I just selected the range of voltages that I wanted, which just happened to be from 50 volts. I think I went up to 140 volts. So all those values there that I just highlighted had to be keyed in one at a time. I know it's laborious, one at a time, into the data monitor of the PLC program. Now let's go back to the PLC program right quick and take a peek. Now I'm not connected to the PLC right now. I'm doing this part of the video. But you go to my data view, and here, starting at this address right here, you can see the values that I put in. This is for the voltages that showed up on my spreadsheet. Let me go like this a little bit smaller. See if I can pop the spreadsheet open over here. All right, you can see for 50 degrees, this is 50 degrees, the data word for 50 degrees. I have a 1.321. So over here in my spreadsheet for 50 degrees, you can see that I have a, add a decimal to this column here. Format cells. This is numbers. Okay, there we go. So with my spreadsheet open, now you can see on my data monitor, the new value that I was putting in was 1.321 for 50 degrees Fahrenheit. Over here on my spreadsheet for 50 degrees Fahrenheit, I calculated that voltage would be 1.321. Now then, for 51 degrees, I calculated it to be 1.347. And over here, you see it's 1.347. So I had to manually take these values here for the temperature range I wanted to check and enter them over here manually. Now once I had those manually in and I was connected to the PLC, then I could tell it that I wanted to edit and write all these values in. All right, back in the PLC program, I want to go to Monitor, and I want to go to Data View and show you my data view. Now you can see my data view is full of data values all the way through here. I have values in new value and current value. I haven't showed you how that works yet with the write. So let me close this data view, and I'm going to go to Monitor, Data View, and I will add a new data view. And this will be Data View 2. And this one's just going to be junk stuff that we're going to do here. I will call this DS200. And you see the current value is 0. So if I've got DS200 here. So now if I have the current value of this and it says that it's an integer because it's a single word, let me click on this one. While I have it highlighted, I'm going to do a fill down. Every time I hit it, it goes to the next data word. Now I have 8 consecutive integer words in this data view 2. I'm not really going to use this in the program, but I want to show you something here. Right now you can see the different columns are address, nickname, and you know the nickname comes from up here in the program. You go to Program and Edit Program Picker, and you put in whatever nickname you want. The current value is 0. I want to put something in besides just zeros in these. Maybe I want 200 to start off with a value of 10 and 201 to start off with a value of 36 or something like this. So what I do is I click on this Edit button and I add a couple of columns. I add in the new value column and a write column. So this new value I set on this one, let me put in a 10 for example. Now I have a value of 10, but it's not in the current value yet. But if I double click on write, it puts it in there right now. And you saw it, maybe you saw it quickly turn red. When it turned red, it means that data is changing to a new a new value right now. And let's say number DS201, I said a 32 or a 36, something, we'll call it 36. And the same thing, I go over here, I can double click write. But now then, what if I have a whole bunch like I had over in data view 1. We'll call this one 287, this one is 98, this one is 30, or whatever, just different numbers, whatever they are, it doesn't matter. All right. So now I have all these different numbers here. So if I wanted all these numbers to go over at the same time, I click write all new values. All right, well, when I click that, it comes up and it says, note, the multiple edits will not happen simultaneously. That means it won't happen within one scan, but they will be written one at a time. Do I want to go ahead and do it? And I'll say, yes, let's do it. Okay, so now you see all these values that I typed in here now went in there, and they are now the current values. So if I take edit back off again, then I'm back in this position here where I cannot change those values anymore unless I go into the edit screen. So I'm going to close this. And I'm going to go back up to my monitor and go to data view number 1. And you can see data view number 1, I have all these values right here that I manually put in, and this came from my spreadsheet. These are the voltage values that I was expecting for these different temperatures. For example, at 50 degrees F, I'm expecting 1.321 volts. And at temperature of 60 Fahrenheit, I'm expecting 1.591 volts. So you can see that all these values here are now in the current value column. But I don't want to change those anymore since I've put them in one time. I'll turn the edit off, and now they're just showing up in the date and now they're just showing up in the current value. So if I go down all the way down to the end, you say I could have put in as many as 100 rows of data in there just in one data view. Now I could have more than one data view. I could fill this one up completely with 100, and I could go to data view number 2 or 3 or however many other data views that I wanted and put more and more in there. So I could have hundreds and hundreds of values that that I put in from a write into the current values. Anyway, let's go back up here. My program is running right now, and you see my raw temperature is 87. It's fairly warm in the shop now. I just came in and it's been in the sunshine all day. My input that I'm reading back from the thermistor, this is my real value in percentage. It's reading 46.8% of the 5 volts. So now then I have the value in my pointer. Right now it's showing 135. Raw temperature I said was 85, or now it's 85. It's cooling down a little bit, and now I did actually turn the air conditioner on in my shop. All these values are fixed. And now if I'm at 85 degrees right there, then 85 degrees coming down here, if I scroll on down, there, 85 degrees is supposed to be 2.32 volts. And so if I come back up to here, look at my percentage, if I take 46.3% of 5 volts, it should be equal to that. Let's take a look at how the program works, step by step. Going back to the main program, rung number 1. This is where I put my output, analog output for the plus 5 volts at 100%. I only have 24 volt supply, which is required for the PLC, but the combo analog input cannot accept a voltage greater than 5 volts. And remember, that's what we saw when we looked at the specifications. 6 volts was the maximum on any input. Therefore, I'm using a spare analog output as the VCC supply voltage for the thermistor circuit. Here in this command, I'm saying copy whatever's in DF10, whatever value is in there, and put it in here in DF3, which is my output. Rung number 2. Now then, I needed to scale the input value from DF1, that's my analog input, to volts. Because remember, DF1 is a value that represents 0 to 100%, and it's expressed as 0 to 10,000, which represents 0 to 5 volts. So here I had to do a little bit of math. I had to take DF1, which was the percentage, and multiply it by whatever DF3 is times and divide it by 2,000, and that will give me my volts in. Now we're going to test this on the data table that I set up from DF100 to DF199. Let me go back now and look at the subroutine temperature. I'll double click. Now starting off on rung 1, I put 50 in as the initial temperature because I was not expecting to measure a temperature below 50 degrees. And then I go to 100 is the DF value for the first address I'll be testing. And DF100 contains the input voltage value I should have for 50 degrees F. Now that was what we saw back up here in the monitor. I'll go back one more time real quick. At 50 degrees F, that's in the voltage value that I'm looking for on that is in DF100. I'm going to turn my edits off right here. All right. Now then, I'll go back. Now then, I'm taking 100 and I'm putting into my pointer DS3. Let me scroll up a little bit. Now then, in rung number 3, this is the beginning of my for next loop. I set it to 90 because that was the full temperature range I was measuring from 50 degrees to 139 F. So what do I do inside this loop? Remember right up here in DS3, we put a value of 100 in. I'm looking for data address DF100. Now then, I'm putting it, copying whatever value that's there, and I'm putting it into DF99. DF99 is what I'll use to compare every time it goes through the cycle. So every time it goes through this for next cycle, this DF number will change from DF100, DF101, DF102, and so forth, and each time that will be put in DF99. Coming down to rung number 5, and each cycle I compare the input voltage against the value I place in the DF word. If the pointer DS3 is 100, then the temperature value I would be testing would represent 50 degrees F. Therefore, subtracting 50 from the DS3 value is the temperature. But this value is only put in DS10 if the input voltage is less than the reference voltage. In other words, once the voltage in is greater than the thermistor resistance, the value DS10 does not change. That means once I get up to what the current temperature is, this will not change anymore. So what I'm looking at here is I'm checking the voltage in against the thermistor reference voltage for whatever degree Fahrenheit that is. And if this is less, then I'm going to go ahead and put it into DS10 for my raw temperature. Now I'll continue doing this each cycle of the for next loop until the voltage in is greater than what this is. All right, so then I also do the same thing down here. I check voltage in to see if it's greater than what my thermistor reference is. If it is, then I'm going to increase my pointer value. At the end of doing this 90 times, then I'll come off the next statement and I'll go to rung number 8. Now the loop is finished. The raw temperature is in DS10, but if this value does not equal the ambient and an offset is added in, that would be in DS11, putting the result corrected temperature into DS12. I'm always going to be adding my raw temperature to my offset, and that's going to equal whatever my ambient temperature is, or the temperature that I display. But let's say, for example, it's 77 degrees. It was what you measure with a truly accurate device, but this is showing you that you're at 78 degrees. Then you can make DS11 be a -1, for example, and you would do that up here in on data view number 1. You would come in here to your temperature offset. You would have it on edit, and then you would add in, make this one right here say a -1, like so. And then I would come over to here and I would write that value in and would make that a -1. And now, even so, my raw temperature is 86, my actual temperature by Fahrenheit is 85. That completes the program. It's a simple program by the number of steps that we've got, but actually there's quite a few things to think about to make sure it works right. But what this becomes is a perfect example of using a pointer to select and go through a for next loop to select the values that you're actually looking for. And in addition to this, this allows you to measure ambient temperature without purchasing a temperature module. One more thing to think about is, I know the program is very, very short, but don't forget, when we go into the temperature subroutine, we are doing this 90 times before it comes out. We're going through those. So 90 times these 3 or 4 rungs, or 5 rungs in here, then that's a lot. That's several hundred rungs. let's take a look at what our scan time is. We'll go to Data View from the monitor, Data View 2, and I will put one in right here. Let's see. System data is SD. There it is down here. And let's spread this out so we can see the words a little bit better. All right, current scan time is SD10. Let's click that one, put that one in there. And I can see right now I'm running 68 milliseconds. So that's still good. Still good. Well, I hope you've enjoyed this video. This video, like I said, is a perfect example of using a pointer addressing inside a Fornex loop to make a selection from different values that you have. The program itself, like you saw, is very simple. There's only, 3 rungs in the main program and 8 or 9 rungs in the subroutine program. But overall, it covers a lot of territory within just a few rungs of programming. These PLCs are very small, but they're very powerful. For example, on this one, I'm only using 1 analog input and 1 analog output. It still has 4 discrete inputs and 4 discrete outputs. The outputs could be for a light to turn on to say that the system is operating, something to say that the temperature is in control or out of control, out of the range it's supposed to be, for example. It could be to start and stop fans. It could be to stop and start some heating or cooling elements. Also on the inputs, it could be for the system is being told to cool, to heat, fan running detection of what we call a flag switch, something like this, a safety switch also possibly coming into it. And at the same time, you still have an analog input and an analog output. Now the analog output could be, for example, used for fan speed control or a heating element control, something like this. So you still have a lot of possibilities. And the thing is, you're only using one little PLC. One PLC, and that's all. So enjoy the videos. I hope you learned something from this. And contact me if you have questions. God bless you.